The math is not mathing anymore.
Hello, I'm Jack. In a previous video, I talked about how to create truchet-tiles. In this video, we're going to take a look at how we can add a organic feel to the truchet-tile. So it's not perfectly round. Instead, let's add a little bit more randomness to the pattern, to each stroke. Let's dive right in. So first of all, this is a previous sketch that we had, which creates a truchet-tile. If you need a refresher, I'll add a link to the previous video. I highly recommend checking that video out before this video. And before we add this, before we work with the pattern, let's first take a look at how we can draw a circle with vertices. And this is actually also something covered in a previous video. I'm going to add another link, but today we are going to focusing on how to create circle with vertices. So first of all, we can obviously draw a circle with let's say maybe ellipse. Maybe I should call this draw ellipse. Draw ellipse just to make it more generalized, not necessarily circle. Ellipse at the center, that is going to be 200, 200. Maybe width is 300 and height is 200. That's the ellipse. But then how do we draw the same thing with vertices? And what are vertices? So for if you want to draw a simple shape, we can use ellipse, rectangle, triangle, so on and so forth. But when you want to draw more complicated shape, we can also use vertices. We also use a function called begin shape and end shape. In between, you can specify the vertices in order to draw the organic shape you want. But we want to start with a ellipse and then add some randomness to it. And so that's why we are starting with how to draw that ellipse with vertices. So first, let's take a quick look at how vertices work. So begin shape and end shape. This encloses all the vertices that you have to create a shape. So let's try to add a vertex with the vertex function. Let's say if we have one at the top left corner, 0, 0, nothing's going to happen because that's just one vertex. And if we add one at the bottom right, 400, 400, we're going to add a line. So whenever we create a new vertex, it's going to connect all these dots. So maybe instead of 0, 0, let's create that as 100, 100. And then instead of 400, maybe it's had 400, 300, and then 100. So we have a line. And then we can keep going. Maybe 300, 300. We draw continually, we draw another line. And then if we add one to the left, 100 and 300, we kind of have a square. If you want to close this, let's increase the stroke so it's a little bit clearer. Stroke weight, change this to 10. You see how there's no stroke on the left side. That's because we started at top left corner. The first vertex, second vertex, third vertex, fourth vertex, but we never closed it. We can either specify the first again in order to close it, or we can use we can add close at the end shape, and that draws it as square. So how do we generalize into a circle? And in order to do that, we need to first take a look at how we can break down a circle or ellipse into vertices. Let's take a look at the whiteboard. So this is a circle, and let's think of this at the center, and like so. So if we want to break this down to vertices, we can start from here. First vertex, maybe having a very low resolution circle. Second vertex, third, fourth, fifth, sixth, seventh, eighth. So we really need that 8 points. to create this circle, and then we can increase the number of points by, if once we have that formula, once we have that algorithm, we can then increase the number of vertex and do the same thing to create a more circle with more fine details. So how do we get these get the position, the x and y coordinate of each vertex? So this first one, it's really about, if we think about it, each one of them is at a different angle. This line is at a different angle. So if we consider this line, if we think of this as a starting point and consider this as theta, this angle, then what we get is we need to calculate the x coordinate and y coordinate. So the x and y. What is going to be the x? The x coordinate, if we think of this as the unit circle, meaning the radius is 1, then the x, which is this side, so the radius is 1, or I mean, we don't need to worry about the radius. The radius, we can actually add the radius. So the theta, this line is really, if we look at that, that's the cosine, that's the radius times cosine theta. Yeah. So sine would be this would be the side of the triangle opposite to the angle, and then divided by the longer side. And so if we want to get the y, that is going to be sine theta. And to be more specific, if we consider and yeah, I think that's actually perfect. I was thinking about the negative versus positive, but this we are looking at exactly the positive side. So these are the exact equations that we need in order to get x and y. And if you think about it, as the angle increases, let's say the angle increased to this point. Maybe I should use a different color. Once the angle increases to this theta, and then if we apply the same formula, the x is going to be cosine, so cosine this angle, that is going to become negative. So because sine wave, yeah, this is kind of getting a little more complicated. So this part is exactly, this is pi, which is right at the center. That's around here. So that means, oh, right, that's yeah, we are talking about the cosine. So for sine, that's going to still be positive. Yeah, so for sine, this angle is still positive. But for cosine, which looks like so, the cosine graph, I don't know if I can match that. Yeah, cosine, I don't think I drew it properly. So cosine looks like this. Because here, right now, yeah, if you actually look at this, this is 0, this is half pi, or this is 90 degrees, this is essentially 135 degree. So this will be the 90 degree, this will be 135 degree. So wait, that means cosine r. Why is x negative? Right here, this is pi. Huh. The math is not mathing anymore. The x, so the y, we just got it. The x theta right here. So it's still positive. But over there, that's negative. What did I do wrong? Yeah, if you know why, I can imagine there's probably going to be a lot of comments uh, telling me what's wrong once I post the video, but I really can't think of what is going on here. X cosine theta. Okay. Maybe we're going to let's get back to the coding, and maybe soon we'll find out the answer. So let's try to plug this function in and see what's going to happen. Yeah. So the x is going to be I times cosine theta. Y is going to be r times sine theta and r times cosine theta. So once we get back to the code, let's try to, instead of this square, let's try to use a for loop. Let's create a for loop and let I equal to 0. Let's use I as an index for the vertex, and then I smaller than the number of vertices. So I'm going to, I can make this variable a global variable. So vertices number, that is going to be, let's say 8, as we did in the graph. So when I is smaller than vertices number, I plus plus, we're going through each vertex, and then so we get x as r. Again, we need to then define r. So r maybe define r instead of draw, so we can use that based on the width or height. So r equals to for now let's use a fixed number. So r times cosine theta. But then what is theta? So this theta is going to be I divided by vertices number times 2 pi. So I usually also like to create another variable called progress or percentage. Progress, that is I divided by vertex number. So this progress is starting from 0 all the way to almost 1, to from 0% to 100% progress. Yeah, so that the range is going to be about from 0 to 2 pi. So theta, so now we have theta, so cosine theta. And then cosine y equals I times sine theta. And finally, we can use this x and y. X and y. Oh, so right. So what happened here is because I'm using the top right now, I did all this equation, and what is going to happen is the 0, 0 is going to be the center of the circle that I'm trying to draw. But instead, I want this, if I want to draw to the center, then we need to add a offset. Yeah, because all this, yeah, when we are drawing this in this graph, it's really drawing around the origin. So now if you want this to move, we actually need to adjust this. So I'm going to add, we can either do a translate. Shall we do a translate? I think I'll try to avoid translate in this case. So going to width divided by 2 and height divided by 2. So move this to the center. And now it's super big. Why is it big? Oh, the R right now, R is 300, so of course it's going to be bigger. So let's say make R only 100. Perfect. And ellipse. So if we want to follow, and one other thing is we used R because we are assuming we are drawing a circle. If you want to support both width and height, then instead of R, we can use the width and height that we want to use. So the first value, that is going to be the width. The second is going to be the height. But what exactly going to be the width and height? If we are trying to recreate this ellipse, then the width is really going to be 300 and the height is going to be 200. Oh, I made another mistake. Because we're talking about the radius, so these numbers should really be the half. So width and height still doesn't change, so, but whenever you do this calculation, that should be divided by 2. Yeah, so now you see how this rectangle and ellipse really match each other. And if you want this to be a more detailed circle or ellipse, we can simply increase the number of vertex numbers. So 16, 32, or 100, that become like almost exactly the same as the ellipse. So now I can delete this ellipse and I still have the ellipse because now I just used begin shape, end shape, and vertices to create this vertex. To create this ellipse. And of course, we can make a circle by changing width and height to rolls to 200. So why did this math here not make sense for some reason? Um, yeah. Oh, I see. Actually, I see why. That is because of the coordinate. Yeah. So it is important to draw the coordinate in the right way. The reason why in this graph, this version, when we have the theta kind of become negative is because the whole coordinate that we are using inside of P5, this is X, this is Y, and it's opposite of the regular Cartesian coordinate system. So in that case, it should follow the exact same thing here, meaning this should be the coordinate. So this is X and this is Y. So now this theta, which is 135, yeah, 135 degree, or that can also be that is essentially also pi times 3 divided by 4. 3/4 of a pi, essentially, which is right here. And that is indeed negative because the positive is at the bottom, negative is at the top, and that's why that is the case. And in the case of cosine, but essentially the graph is going to be different. Yeah, the cosine, because so usually this sine wave that I used to draw, sine and cosine that I used to draw, is really based on um, the Cartesian coordinate system that we use. That's why like everything here it looks a little more counterintuitive. I'm not even going to try to attempt to draw the sine wave in this in here because it doesn't look like that's gonna make sense. I'm not. Hey, future Jack here. I was a bit clueless when I recorded the video, but I'm gonna try to attempt to explain it again. So when I talk about this angle, which is 135 degrees or 3/4 pi, this angle theta, uh, and as we can see from the graph, this is x coordinate, this is y coordinate. So when the theta equals to that angle, we know that the x coordinate should be negative. I was trying to figure out why that is negative. And that was because I was not thinking right about this graph right here. So for x, we have the cosine theta. So cosine starts here and looks like so. So when x equal to 0, when the theta equals to 0, the x value is 1. So when theta equals to pi, x equals to -1. So when theta is 3/4 pi, it's actually located right here. I think in the recording, I kept thinking here because I was starting to count from here. So actually, this angle is located right here. So of course, it is in the x is negative, so which is consistent from this graph to this graph. So let's get back to the video since I'll try to avoid the trouble here, but I believe you get the idea how we use sine and cosine to calculate the one thing I will mention is the reason why this r becomes width and height is that this r here, width and height, that is actually also a little bit difficult to explain. This is the width. This is the width. And this is the height. And maybe the angle I'm using is not exactly right. I'm doing another smaller angle. I really should have rehearsed this. When it's narrower. I'm not gonna waste time on this. This my code is working. Let's not worry so much about this. But you get the general idea. And we're gonna get back to our code. So the width and height. So now I can prove to you, as we did earlier, if I change the width to be wider, it's going to be wider. If we change width to be narrow, it's going to be narrow. So it works. And so now we have this powerful tool, which is those vertices to create the circle. And with that, we can then adjust the vertices in order to create more scribbly lines. So instead of perfect circle, we can add in some randomness. So how do we add the randomness? Let's apply the randomness to the width and the height. And in order to draw this, I'm going to add some randomness and apply that to both the width and height. So random, maybe I'll call it a size factor. So a factor or multiplier that affect the size. So that is going to be a random function. And I don't want it to be 0 to 1 because that's too big of a change. I want to change maybe between 0.5 to 1. Yeah, so it can only be as small as half of the original size, as big as the same original size. We can still tweak that number a little bit later. So x and y, essentially we want to multiply that to the width and height. So multiply it here, multiply that here. Yeah. Oh, that's actually a hapless accident. That's a pretty interesting effect. But we are going to oh, I forgot to save this version. So I'm going to say let's actually save this version. So I'm going to copy the code, revert it back to the previous version, and then duplicate this. Yeah. So this time, and then paste the latest version. This time, this is going to be using vertices with randomness. So what I'm going to do is maybe we can even keep this randomness. This is let's keep this version. Why not? Happy accident. This is a pretty cool effect. And I'm going to duplicate this again and get back to what I'm actually trying to achieve. And no loop, which means the draw function will only run once. So this is one iteration of every time you refresh, you see one version. And what we really want to do here right now, because we have too many vertices number, too many vertices. So if we reduce the number, well, that's where it's So now this feels more like a regular circle. And but of course, it doesn't look very smooth because we are using straight lines to connect them. One really simple way to make them round is to use curveVertex, like so. Refresh. But curveVertex does not like this close part, because the close, essentially what close does is to abruptly connect with a straight line at the very end. So if we remove this, you see how this is what it looks like without the close. So if you simply connect it, it will not look smooth. And the trick to make this work is actually that trick will not work in this case. So usually the trick I do is time 3, but then the last one is not going to match. I think this is one of the cases where using something like Perlin noise can really easily avoid this issue. But when we apply this to the true shape pattern, we will fix it with another issue. So this is not this is a problem for drawing a round round shape like this, a blob-ish shape like this. But you will see how we can solve this in the other version. Let's actually try to solve this too here. Essentially, what we want is that in the very first vertex and very last vertex, we want it to be the same. Yeah, that is a little. Let's do this. Yeah. First, I think it's necessary for me to explain why I add +3 here. And that has to do with how curveVertex work. And let's switch back to the camera. Going to try to use extra room. So the way curveVertex work is that in order to draw a curve, you need at least 4 vertices. So when you have one vertex, second vertex, third, and fourth. So when you have 4, there's this algorithm that's used in here, which is essentially trying to create a round curved line based on all the vertices. So this will be roughly what the curve looks like, because it's trying to create a curve that controls all this. So the last point, really what it does is to control this curve. So the last and first one. So if the point is here, then the curve is going to be a little bit different. So depending on where this point is. So which is why when you have four vertex, you only have a small curve. And when you add another vertex, this is going to be curved. When you add another vertex, this is going to be curved. So there's only 2 missing. And this is why when I did +3, I'm trying to add 3 additional vertexes. I think at this point, let's clean this up. Let's wipe all this out. So we are trying to draw a circle. Let's again use that simple 8 one. So starting from maybe the right side, this is the first one, second one, third one, fourth, fifth, sixth, 7, 8. Yeah. Remember how the first one and last one are ignored? That's why at this point, this is the curve that we have. This is the curve that we have. But if we simply by adding to that upper range of the limit of the for loop, what we are doing is to let this curve continue. So we end it here. So essentially, let's use another color. We are saying keep that pattern going, but repeat more. So I'm adding another point. So that's where it draws this part. I'm adding another point. That's how it completed here. And that's another point. This is why I'm adding 1. I'm adding 1, 2, 3. I'm hoping this to complete. But the issue here is when you draw a circle, that's perfect. We can actually prove in a second. But now, because we added randomness, what that means is these points do not match. That's why this first one and the last one, they are not matching, because we had randomness for every kind of the radius or the size. We are using both width and height. So there's some randomness involved. So that's why the first one and last one does not match, because the first random number and last random number does not match. So if we want this to close properly, really what we need to do is to match that random number. We can try to solve that. So that really kind of become a different video. That became like outside the scope of what I'm trying to do. Maybe you can skip this part if that's not what you're interested in, and skip directly to the truchet pattern part. But I'm going to discuss how we can solve that. So let's get back to our code. And just to quickly prove my point, if I change the size factor to 1, which means there's no randomness, it's a perfect circle. So like I mentioned, if this is 0, there's something missing. If this is 1, closer, 2, closer, 3, that's when it perfectly closes. That's why I added +3. But because there is randomness, it does not perfectly close at the very end. So how can we make sure that this blob perfectly closes? So with randomness, ellipse using vertices with randomness, and then not closing. This is the one that's not closing. Let's try to close it. So if we want to keep the same randomness, the only reason why this random number is different from when we draw the circle, it becomes different, is because every time we are generating a new random number, and there's no way that first random number and the later random number is going to match. It's always random, so that's why there's that disconnect. So if you want that to connect, one simple way is to pre-generate these random numbers. What do I mean by that? We can create a for loop. We can create a what is it called? An array of random factors, and random factors, and then we can use this for loop. I'm going to write a for loop to pre-generate these random numbers. So let I equal to 0, I smaller than vertices number, and I plus plus. So I'm going to pre-generate this. So this is the exact number of randomness we want, because when we have let's say the 16 vertices, we want 16 numbers, because we don't want more or less. We want to match exactly, each vertex has one random number. So random factors dot push. So that will add, the push will add to the array. What do I add? That is going to be the random number that we generate, which is between 0.5 to 1. And once that is created, we can actually take a look at this. Let's take a look at this random factors. This is a random factor that is generated here. And every time we refresh, it will generate a random sequence. But as soon as it's generated, that is fixed, and then that can be used to create this blob that will perfectly match. And let's see what I mean by that. I'm going to comment out this console log random factor. So now instead of generating a new size factor, I'm going to use this random factor based on indexed. But remember how this time over here we are drawing 3 more vertices. So what do? We use a modulo calculation, which gets our remainder, because we want to make sure the number is always between 0 and 15 in this case. How do we do that? We use to calculate the remainder. So that is going to be I modulo and vertices number. And let's actually create a separate variable for this so it's a little bit clearer to read. So factor indexed is going to be this. So when I equals 0, it's 0, I equals 1. So before I reaches the number of vertices number, it's going to be whatever is I is going to be this index. But as soon as it becomes bigger, let's say 16 modulo 16 is going to be 0 because it's perfectly divisible. So the remainder is 0. And 17 modulo 16, that is going to be 1 because the remainder is 1. That's how we make sure that number always stay within that range. So factor indexed. Now, every time you run this program, it's going to run the sketch. It's going to generate a new blob and perfectly matching that. And that is because whenever we draw a vertex, we are using a pre-generated random sequence. So this is with randomness closing properly. So now finally we just drew a random circle. Why did we do this? Because we want to apply this technique to the arc that we are going to draw to form the true shape pattern. And then of course we can always adjust the amount of randomness. Like this is a lot of randomness, and if you want less randomness, use a smaller range, so 0.9, 0.1. So now it looks like almost a circle, but slightly off. So that's really depending on your taste and just trying things out and see what works best for you. So how do we combine these two? I think I'm going to almost instead of copy paste, which will be pretty hard to follow, I'm going to rewrite that in the other sketch. But I'm going to use this as a reference in case I forget. And this also, yeah, you can choose the number of vertices number. This is less vertices number. This is a lot of vertices number. So that really just changing this number can really change how this blob feels. So back to this. Now we want to replace the vertex. We want to replace the rect. Oh, it's been 40 minutes. It says right here. And we want to replace that. How do we do that? At first, I'm going to, because we're going to add a lot of randomness, it's going to be really hard to see at that size. I'll make this maybe even larger. So this will give us the opportunity, maybe even larger for now. We can always adjust it, make it smaller. So this gives us the ability to really see the fine details. You know what? Can we just try one? Yeah. This will really help us to see the scribbles first, and then we can change the column number later. So really, what we want to change here is to create our own arc function. If you watch the previous video on the true shape pattern, you'll see how when I created the tile, I made that choice of trying to match exactly how ellipse or rectangles work, so that I can simply replace rect with tile and everything just works really great, really well. So now I want to replace arc with my custom arc. So I can, so let's try to write a custom arc based on this other sketch we just created. And let's call it scribble arc. And let's use the same set of parameters. So we have the x, we have the y, the width and height, and then the start and end. Start angle and end angle. And depending on how my math was done earlier, yeah, the start and end, hopefully everything will be fine there. So let's try to do that based on this information. So essentially, and then, we can add another one to define the number of vertices. Yeah, this can, let's start with just a variable. So vertices number, let's say start with something like 8. And then we draw a for loop, let I equal 0, I smaller than the vertices number, I plus plus. And for that each vertex, we try to do the x and y. X equals to w times the keep forgetting this. So let's start with the progress, which is I divided by vertices number. There's typo, vertices number, and then let's get the theta, which is going to be theta is going to be 2 pi times. So here's the thing. When we use 2 pi, that was because we want to draw a complete circle. That's why it's 2 pi. In this case, we are starting at the start angle and end at the end angle. So here this calculation is going to be a little bit different. So the theta is going to be the start angle plus how much we have progressed. So what's the difference? Then the difference, maybe I can even create another variable, the difference, or delta theta. Does that, delta theta, or the, let's call it delta theta. Delta theta is referring to the end angle divided minus start angle, so that difference. So delta theta, because delta usually in math is referring to the difference. This times the progress. And because one other thing that's different is in the case here, this progress here, we really wanted to start from, let's say we start from the first vertex and go all the way to the 8. By the time we reach the 8th or vertex, we want it to be matching this exact angle. And because of that, this progress should not be here, because this progress right now, the progress is going to reach, I guess I can also just add +1 here. Let's see how the things go. And we can potentially just solve that by +1. So progress. And because what I'm concerned about is that this progress, there's a typo here. This progress start at 0 divided by 8. So zeroth of the 8th, 0/8, is that how you say it? And all the way until 7/8. But that means we don't reach the end yet. So we wanted to get to the 8/8 or 100%. So let's try to, I think I did it different last time, but let's try a different approach. I might regret it later, really, but let's see. So that's the theta. Once we have the theta, W times, I believe it's cosine for x, W divided by 2, really important, divided by 2. W divided by 2 times, was that cosine? And then cosine theta, and then we also want to displace it by x. And that's actually alarm, a red flag, because we should not be reusing this variable. There's already x, so this should not be the x. So let's call it vx for vertex x. So that's the displacement we want to get. And then constant vy equals to I divided by 2 times sine theta plus y. So now we have the vertexes. So let's try to draw them. That is going to be vx and vy. And let's also add begin shape and end shape. And right, we haven't really replaced this we haven't really called this function scribble arc yet. But let's see if there's anything else I want to change. All looks good to me, so my hope is I can simply replace all the arc with scribble arc, and this will work. Of course, I haven't added the scribble yet, but let's hope this will work. Replacing all of them. Oh, yes, it perfectly worked. You see how this is formed by 8 vertices. So 3. Yeah. Now I see, yeah, I think this +1 worked, except now the vertex number is always like one more. So in fact, even though we specified 3, in fact, the vertex number is 1, 2, 3, 4. So if you want that number to be exact, we can always, instead of here +1, we really should do -1 over here. Yeah, and let me show you why I want that -1. So without that, it's not complete. So -1, this ensures that it starts from 0% and goes all the way to 100%. So this is 3 vertices, and this is actually 9 vertices or 4 vertices. So we have exact control over how many vertices we want to have. So that's really close, and let's take a sneak peek. So truchet-tiles, grid of randomized tiles, variation, or using vertices, maybe. There's always typos like vertices, yeah. So let's give it a try. If we have 10 by 10, great. This is already a variation. You know, we can reduce. Maybe it looks more interesting. We'll reduce this like 3 or 2. This is where it actually become like those right angles. So that's like fun. So 3. Give it a little bit of randomness and variation using vertices. Yeah, and let's duplicate this. And then again, let's add the randomness with randomness. That's where, oops, that's like what we're trying to get. And so how do we add randomness? That, if we remember, the way we did randomness is by applying a size factor to both the width and height. So let's do that. We create a size factor. And again, we are going to be encountering the same issue we encountered earlier where things don't match, but let's not worry. Let's start from here. So the size factor is going to be random. Oh, I want this size factor to be different for each vertex. I'm going to put it inside of the for loop. So random, and we want that to be somewhere between, yeah, let's start from somewhere between 0.5 to 0.1. We apply this size factor to the width and then to the height. And this looks a bit messy, partially because of that matching thing and partially because we have too few vertices. So if we do 10, that's where it start to look more interesting. And again, I'm going to make this 1 just so that we can focus on just one tile. Now you see how this adds randomness. And but maybe, yeah, let's do 2 so you see how it doesn't match. So it doesn't match. So if you want it to match, it kind of get to the same issue of how you want to match. You can pre-calculate the randomness value like I did in that previous one. However, the problem is that now each tile is unique. Each tile is independent. You cannot pre-calculate. I mean, you can if you want to pre-calculate the randomness for everything, but that's a little bit too complicated. And there's a simpler way and a more unified way. And before we do that, it's important to know how does this truchet pattern, this quarter circle truchet pattern work. So let's investigate that a little bit. So let's simplify with a 2x2 grid. The truchet pattern, the reason why it works, and also the reason why I find it really fascinated myself, is because there's a simple rule, which is each pattern always touches the center of the edge. So no matter which pattern comes next, either it's this pattern, or if you have the other pattern. Because we know that the center always touches, so it really doesn't matter which one of the orientation it is, and always feel like continuous line, and that's why it works. And the reason why it does not work for us right now is because we added randomness. By adding that randomness, these point is no longer at the center, so this can be at any point, at any point. This is at any point. This is at any point. It's at a different position, but you get the idea. So now this point does not match. So why don't we simply enforce this rule that these two edges always stay at the center? And that way everything will happily meet and be continuous. So let's do that in our code. So how do we make sure the first one and second one is exactly the center? That is simply by not applying the size factor, or or making the size factor to be 1 when for the first vertex and the last vertex. And what do I mean by that? So size factor right now is random. So 0.1. Yeah, so it's always random, but what we want to do is if size factor, if the vertex is if the index for the vertex is either 0, either the first one or the last one, we want to make sure that the size factor stays as 1, which means this, the regular part of the arc, which means exactly the center for that arc. So now we will be changing the size factors. I'm going to use let instead. So let, we can either generate that first and then correct that, or yeah. So let's see, let size factor generate whatever. But now if index is the first index 0, or index is the last index, which means that's vertices number -1. If either one of them is true, let's change size factor. So this is one way you can write an if statement. If you put in one line, you don't even need the curly braces. The size factor is going to be 1. You see how now it matches whenever it's 0 or either the first one, I index is the first one, or the last one, it's going to match. So now if we change this to 10, yeah, make this a larger number, it always matches. Even though it looks very, very, very much random, it still matches. So great. Let's duplicate one more. And remember how in this version we are using curveVertex. I want to apply that same thing over here. So how do I yeah, that's why I call it Scribble arc. Right now it doesn't quite look like Scribble yet. So how do I apply that curve? And with curve, because of the reason how curve use more vertices before it forms a curve, there's actually more thing we need to do. But let's first just simply by trying changing this vertex to curveVertex and see what happens. curveVertex. Again, you see something is missing. And let's again focus on just a few of them. I mean, this is also a pretty interesting effect if that's what you're looking for, but if you do want to close it, we want additional vertex beforehand. So we, instead of starting at 0, we can start as -1. And let's see what it, yeah, and then ending at +1. And this is how it matched. Let's see if it actually matches. Let's create this for, yeah, perfect. So I'm reducing oh, this is actually interesting. I never thought about this. Yeah, this is an interesting effect. Are they actually matching? I think they are matching. Yeah, because right now the only curve that we have that is um the only vertex for which has a that has a fixed size factor is zeros, and then the vertex number minus one. Um, so because it started from minus, yeah, so that means this is still the first one, the one that comes before is still random, but then this I think, yeah, because of the way this curve function works, it actually perfectly matches. I'm pretty surprised about this. Let's change this to a smaller number. Yeah, great. Oh, I accidentally added a really large number. This matches, so perfect. So 5 and 8, 8. Yeah, if you want this to be a little bit rounder, what we can do is, instead of start arranging from 0.5, it should be like 0.9 or something. So this means it will, because if this is 1, it will be the perfect round, perfectly round, a perfectly round, two shape like arc. But as we make this difference larger, that's where we kind of add more scribbleness. So maybe point A, just to add a little more. And this really is the curve, the kind of scribble that I intended to create. Yeah, we can decrease the thickness, the stroke weight, maybe to about 3. Yeah, and maybe, yeah, like if you want to the pattern to be clearer, we can do something like this. And so this is how you can create a true shape pattern with some amount of randomness, with this kind of scribbleness. So this is variation resembling, am I spelling? Resembling scribbles. And then there's plenty of potentials and possibilities. This is one example of true shape pattern that you can create based on the quarter circle true shape pattern that we created in the previous episode. We added a little more organic touch by adding randomness to the arc lines, to the arcs, and we had a few different iterations along the way. And I hope this gives you some inspiration of what's possible with true shape pattern, and I would really love to see what kind of pattern you will come up with. And if you like the video, please like the video, comment down below, and if you create your own version, please share your sketches in the comment section. I really love to see what you create. And thank you again for watching this video, and see you next time.